Alright, as we get started, we'll remind you again tonight for your reception at 6:30. The dates and center, Space Rocketcity. Hope everybody will come out and participate there. And also, you notice the presentation is being videotaped. I believe they'll be available online sometime next week at irongeek.com.
I'm looking for that, but yeah.
Okay. So just keep checking back there and see when they're available. My name is Robert Allen. I work at Dynetics, providing business development support to our enterprise solutions unit. And I'm happy to introduce Mr. Scott Hogg, who is Director of Technology Solutions with Global Technology Resources Incorporated. The founding member of the Rocky Mountain IPv6 Task Force, member of the InfoBlock's IPv6 Center of Excellence. Scott has a BS in Computer Science, along with a Master's in Telecommunications, and many vendor and industry certifications. He's authored the Cisco Press Book on IPv6 security and writes a popular blog for networksworld.com. Scott has enterprises and service providers for their IPv6 planning, training, and deployment. Please welcome Mr. Scott Hogg to talk about the transition to IPv6.
I know what you're thinking, like IPv6, gosh, I heard about this in 2003. You know, it's been coming any day now for like a decade. So, yeah, after I got my CCIE, I kind of wanted to learn things that didn't involve an exam or a test or anything like that. And so I started to learn about IPv6, you know, 99 and 2000, and I got really excited about it. Okay, any day now, you know, so I started teaching classes on the protocol, and as I started to learn more about it, I realized there were very subtle differences between that and IPv4, and you know, as IPv6 has kind of grown in adoption over the past decade or so, you know, the protocol stacks have become more mature. It's become, you know, a little bit more used out there. But what's interesting is it's largely a protocol that many security practitioners haven't spent much time learning about, and it represents some security implications for our network systems. So I like to start off my IPv6 presentations by saying, even if you haven't started using IPv6, and I know many federal organizations in this room say, we haven't used IPv6, so why would we consider the security of it? But I'm basically stating that you have IPv6 running on your networks today. You have IPv6 enabled operating systems in your pockets, on your desktops, you know, in your server farms, and you haven't done anything to secure it. It's a protocol that runs in your environment. There are IPv6 packets on your Ethernet networks, on your wireless networks, and yet there isn't anything that has been done to protect it. And so there's essentially this latent protocol that's running inside of your environments. You all use these types of modern operating systems, and because IPv6 has been incubating and maturing for more than a decade, it's been put into the endpoints. So IPv6, I think, fairly early on, suffered from this logjam that occurs, you know, because it wasn't just IPv6 wasn't just a system that we had to deploy in the core of the network. It wasn't just something we had to upgrade endpoints. We also had to upgrade content on the internet. You know, it was a lot like when we moved to high-definition television sets. Many of the older folks in the audience know what I mean when I say change the channel. That was the way we did things when I was a kid. When we moved to high-definition television, it wasn't just about replacing the television sets in people's homes. It wasn't just about getting content to be shown in high-definition resolution. It was also about, you know, upgrading the infrastructure, the broadcast airwaves, or the satellite link, or your coaxial, you know, RF connection, you know, to your house. And IPv6 suffered from this early on in its infancy. So we needed to have IPv6 enabled in operating systems. We needed IPv6 content on the internet, and we needed service providers to embrace IPv6 and deploy it. So So now that time has gone on for the past decades, IPv6 has made its way into our operating systems. It's made its way into service provider networks, and now there's content on the internet. Many of the most popular websites on the internet now run IPv6. Google, Facebook, Yahoo, Wikipedia, Bing, lots of sites. And to give you some statistics, IPv6 is about 5 to 7% of websites. The Alexa 1 million websites run IPv6. Of the 48,000 autonomous system numbers on the internet, I'd say a fifth of them are advertising some IPv6 address block to the internet. All of the internet exchange points can communicate IPv6. All service providers have some form of IPv6 connectivity. And we have IPv6 enabled operating systems in our environments in enterprises. But enterprises haven't turned on IPv6. They haven't enabled it on their routers, across their WAN, across the internet perimeter, but there's this protocol that runs. So today, you've got these operating systems inside of your network, and they are running IPv6 by default. That's how it comes from the manufacturer. You probably haven't done anything to turn it off, like set a reg key with a GPO to say turn it off. And when your users go to www.google.com, those operating systems are doing an A record and a quad A record lookup. And you're getting back a v6, record, DNS resource record. But your operating system knows it's on a v4 only network, so it makes the connection to google.com or IPv4 transport. When your system boots up, when these operating systems boot up, they send out ICMPv6 messages on the LAN to try to determine if there's an IPv6 capable router. They send out an ICMPv6 type 134 router solicitation message when they first boot up or join a wireless network or what have you. And they expect to hear back a routing advertisement message, an ICMPv6 type 134 message from the router. And that routing advertisement would then give clues to the operating system about how it should go about bootstrapping itself and getting on the network to obtain an IPv6 address. It would tell it whether it was going to use DHCPv6 or it should use stateless address auto configuration and just come up with its own address. The router advertisement tells the hosts, hey, here's the default gateway, here's the router that I'm going to use as my first hop for getting off net. And we have a neighbor discovery protocol built into IPv6 that uses ICMP version 6, neighbor solicitations and neighbor advertisements, which is the IPv4 equivalent of ARP, which you're all familiar with in IPv4 environments. It's called the neighbor discovery protocol, and instead of an ARP cache, now it's called a neighbor cache. It's a little bit different terminology, but it's a different way of doing ARP, essentially, with IPv6. But it uses multicast, and it uses the ICMP protocol. Rather, where IPv4, it used broadcasts, and ARP was a separate function inside of the IP stack. It didn't rely on ICMP or any other sublayer in the network layer. And so you have systems on the network that are configuring themselves with linked local addresses. The FE80, you see that often, right? You see that it has an FE80 address. And people say, oh, I have IP6 running, see, FE80? Well, the linked local is an address that all IPv6 nodes configure themselves with upon boot up or instantiation or connection of that interface. Whether it's connected to an IPv6 network or not, the linked local is the address that you need to get an address. It's the address that you use to source those ICMPv6 messages from to kind of start this process. But it is a valid unicast address. You can communicate with that FE80. Other systems on that network can talk to each other's FE80 address, even if there's no default router sending routing advertisements down to those hosts on LAN. And you have this chitter chatter on the LAN with this multicast and these linked local and this ICMPv6 messages on LAN. Hosts are doing duplicate address detection. So instead, when they instantiate themselves with an address, even their linked local, they send out a neighbor solicitation for their own address. They don't hear back a neighbor advertisement for their own address, therefore they know it's okay to use that link local address on that link. It just helps avoid collisions. With IPv4, when two hosts assume the same IP address, kind of they both get clobbered, right? With IPv6, it's a little more orderly than that. So you have these little errant IPv6 packets on the LAN, and in fact, if you have Microsoft operating systems, Server 2008, 2012, doing clustering, they discover each other on the LAN, they discover each other's link locals, and they actually are using those link locals to communicate with each other on the LAN. At your house, you have link layer multicast discovery protocol. You have other kind of people near me, peer neighbor resolution protocol. You have these plug and play type protocols that are in a home or also in a business environment that are active and actually use IPv6. And the whole point of this is that the operating system is trying to facilitate getting the user to both internets, the v4 internet and the v6 internet. And they often try first IPv6 if they can, and then fall back to IPv4. And many of these operating systems create tunnels on behalf of the user. If an operating system thinks it's on a v4 only service provider, it may try and tunnel the v6 traffic inside of IPv4 traffic and send it over that IPv4 service provider to get to some gateway or relay that then bridges that v6 traffic to the internet. And this all happens without administrator, without end user configuration. Because I tell my mom, the internet's running out of phone numbers, so we're going to IP version 6. I don't want to have to tell my mom how, she needs to go to this website because it's IPv4, or this URL because it's IPv6, or run this version of a browser because this goes to the IPv4 internet, and this version of a browser that goes to the v6 internet. We want to make all this seamless to the users, and so the manufacturers and the IETF, the manufacturers, we've implemented these techniques in operating systems to facilitate better end user experience. And what I mean by happy eyeballs here is RFC. Years ago, operating systems very draconianly preferred v6 over v4. But if v6 connectivity was faulty, it would wait, time out, before it fell back to IPv4. And so what we wanted to do is make operating systems we don't want to penalize people if the v6 is faulty. v4, or v6, should be as fast as v4. And we shouldn't have the draconian preference if v6 is faulty, we want to fast fall back to v4 if v6 is faulty, and we want to cache that result. So when you do a get a host by name, it sorts that ordered list of addresses that get returned. It sorts the v6 at the top, and the v4 addresses further below when you do a get host by name. What we want to do is order that list based on best performance. So Happy Eyeballs is an RFC. Many browsers have implemented that. Google Chrome, others, Firefox, other browsers have implemented that. Inside Apple, Macs, it does a different process where it kind of does a race condition. Inside Windows hosts now, if you have Windows 7 or Windows 8, you have this thing called the Network Connectivity Status Indicator, NCSI. If your system tries to go and make a v6 connection to ipv6.microsoft.com/ncsi.text behind the scenes, and if you can get there over IP, it's an IPv6 only site that Microsoft maintains, and if your operating system can get there over IPv6, then it knows that v6 is good, and then it keeps IPv6 addresses at the top of that order list. So that's called happy eyeballs. All this is going on kind of behind the scenes to facilitate making it easy for end users to get to IPv6 internet content. And so many people don't know that this is happening, and it's difficult to tell when a web browser is making a connection to Facebook over IPv4 or Facebook over IPv6. The end user doesn't know any difference. Facebook has an A record and a quad A record. Browser does a DNS lookup. It gets back an A record and a quad A record. It may try to make a v6 connection or a v4 connection. It may have activated tunnels or not. And how do you as an administrator know that like half the page was rendered over IPv4 transport, half the web page was was rendered over IPv6 transport, the web browser just assembled all those components into the page and rendered them in a single view. But the page could be mixed content. Each one of those TCP sessions could be a different IP transport version. And so all of these things are going on inside the operating system, and it may create tunnels like Teredo tunnels or 6-to-4 tunnels on your behalf. And these techniques are there. So basically, if you're not protecting your IPv6 enabled network, you haven't taken any steps to secure it, there is this latent threat that exists. There's a protocol in your environment that's running, it's active. There's things inside operating systems, mobile operating systems, laptops, server operating systems that are trying to facilitate and communicate. And so basically, we have IPv6 in our environment. We lack visibility to see what's going on. We don't know if hosts are talking on LAN with each other, and we don't know if maybe there's tunnel traffic. So there's an invisibility here. And so that is kind of how I'm going to set the stage for this presentation. So as there aren't a lot of attackers focused on IPv6. It's probably the same number of people as IT administrators who are knowledgeable about IPv6, all things being equal. So if it's only 5% of the IT administrator population who are knowledgeable and cognizant of IPv6, maybe it's only 5% of the attacker population is interested in IPv6. When only 2 people have MacBooks, not so big of a target. When millions of people have MacBooks, it becomes a bigger target. When a few people are using Mozilla, its attack value is low. When millions of people are using Mozilla, it becomes Firefox, it becomes a higher target. So just like anything else, IPv6, as it grows over time, will increase as a target. We can see, that there are security attack tools that have been developed either by security researchers or attackers, and we get an idea that it's an active area of security research. Not just a few years ago, IPv6 traffic volumes, like as reported by Google, were only maybe half of a percent of the v4 traffic volumes. And then it went quickly to 1%, and then here just earlier this year it was 3%, and now it's heading to like maybe 5-6% by the end of this year. So we think that maybe by end of 2015, it could be maybe close to 10% of all internet traffic is IPv6 traffic that's going on kind of behind the scenes. And for every Facebook page that gets delivered over IPv6, it's one less Facebook page that got delivered over IPv4. So you'll see there's this tipping point that'll start to occur. It doesn't take a lot of v6 capable systems and v6 enabled content to have this tipping point effect. And now every year, IPv6 traffic volumes are doubling. So it went from 3 to 6, 6, next year it'll go to 12, 12 to 20. I mean, it's basically on a curve like this at this point. And so, like other talks today that you've heard about things that are active and attacks that are actively taking place. With IPv6, what I'm trying to do with this talk is to educate you about something that exists ahead of when the threat may be realized. Or we see indication from these attack tools, and we see indication that these things exist. We see that now, a lot of these tools are now integrated into Kali Linux and stuff. We see that IPv6 is gaining the interest of attackers, and we started to see DDoS attacks that that are comprised of IPv6 traffic. That could be one of 2 things, right? It could indicate that an attacker just happened to enter in a URL in their attack tool, and that URL came back with a collided record, and the attack just happened to take place over IPv6 traffic, because that's how things work. The attacker was clueless and didn't realize that actually that site that they were attacking was IPv6 capable and serving up a quad A, and the DDoS traffic happened to go over IPv6 transport. Or it could mean that the attacker was clueful and thinking that the victim didn't have a way to mitigate that much, 40 gig of IPv6 traffic. That their DDoS mitigation strategies might only work for v4 and might not work over v6. So, I mean, we see these things on the internet. We see that IPv6 is gaining ground. But what we'd like to do is maybe anticipate the things that an attacker could do and head them off ahead of time. You know? And that's what we want to do. We want to be educated about something ahead of when the threat's occurring. And so I don't have real data here to tell you this has happened, these people are targeting these kinds of sites with IPv6. We're trying to anticipate and look at, you know, what tools exist and look at, well, what are the security researchers finding out about the protocol, and then what can we do to shore things up ahead of time. And so Hacker Choice, IPv6 Attack Toolkit, SI6 Networks IPv6 Attack Toolkit, Foca that was released a year ago at Takedowncon 21. There's scanners. You know, now it's built into many, you know, of the testing tools. IPv6 is built into all the vulnerability assessment tools, and so forth. There's packet forgery, SCAPI, DDoS tools. I mean, so it gives us an indication that it's an active area of security research. One of the things that's different between IPv4 and IPv6 is the fact that the address space is very sparse, very sparsely populated. You know, with IPv4, we have a very dense population. Had Sapphire SQL Slammer worm ran today, in 2014, it might have spread even faster because of the density of the population is that much more. With IPv6, nodes are, well, not only the networks are sparsely populated from each other, but the nodes in those networks are sparsely populated. So, the way IPv6 addresses work is the first 64 bits indicate the network, the geography, and the subnet. The last 64 bits represents the interface identifier. So remember back to the old days of AppleTalk, IPX, where you had network numbers, node numbers. Similar kind of concept here. The last 64 bits is the interface identifier that represents the point of attachment of that device on that network, uniquely identifies, you know, the host portion of the address. So we generally use a /64 as the prefix length for all LANs, VLANs, wireless LANs. That's the standard prefix length. So in the last 64 bits, so 2 to the power of 64 is 18 quintillion. There's 18 quintillion possible hosts on a LAN. You're not going to make networks that big. You're still going to, for every VLAN you have, you're still going to use a /64, but it's only going to have a few hundred hosts in it, probably. But I know there's some people out there that do crazy things like, you know, /22s and stuff like that with IPv4. But still, the network probably doesn't have more than, you know, 300-400 hosts. Nor could you have that many hosts on a network because of broadcast farms and things like that with IPv4. So you're going to use /64 as your default prefix length. You're going to have 18 quintillion addresses. If you allocated every server or as colon, you know, the router would be ::1. If you started addressing your servers or systems sequentially, like ::2, ::3, ::4, trivial for the attacker to find hosts on a LAN and then attack them. But if you use randomized interface identifiers, like either use most all DHCP 6 servers hand out randomized interface identifiers, or you did or you used hosts that were doing Slack with privacy and temporary addressing, they would basically have essentially a randomized interface identifier. On LAN, it could be very difficult to find hosts to even attack them. If you don't know their IP address, you can't attack them. So how does an attacker find and do reconnaissance on the LAN other hosts on that LAN? Well, let's say the attacker, and in order to do these kinds of things, the attacker must be either on link or have compromised a system on that LAN to be able to generate traffic on that LAN, that's multicast traffic, to discover other nodes on that LAN. So the attacker is compromised a host some way, either with malware or directly, and now is going to pivot to other systems on that LAN. And so how do they even find other hosts on that network to pivot to? That's the issue here. There are a bunch of techniques for speeding up this process. You know, systems that don't follow RFC 4443 or ICMP version 6 may respond back to a ping on an Ethernet interface of a link local multicast group group address, FF02::1, that's the all nodes multicast group address. So some systems like Linux systems will respond to that. And when they respond back, now you know their address, now you can attack them. The Hacker's Choice IPv6 attack toolkit has a little tool called Weaponized. Older BSD systems responded to the node information queries. It's like a weird version of, it's almost like another version of Finger on the network. If you knew that an organization used all, Asus laptops of a particular manufacturer, you might know that it had a Broadcom name inside of it, and you would know the organizational unique identifier, the upper 24 bits of the MAC address. If you knew that the network was using EUI64 as the method of coming up with the interface identifier, then you would only have to scan 2 to the power of 24 addresses. Big if. If I knew your V4 address, I might be able, and if I knew you might be using one of these different tunneling techniques, I could guess that V6 address with the V4 address embedded inside of the V6 address and scan for known prefixes and subnets. There's a Metasploit framework auxiliary scanner called IPv6 Neighbor, which basically looks for hosts on a network, finds their MAC address with V4, forms EUI64 addresses with them, and then tries to contact them using the link local address. You can use one protocol to find the other protocol by looking at ARP information and use that to try and find the host of IPv6. Yeah, if you were using certain types of tunneling techniques, we could be able to find you. And really, if you found one node, you could pivot off of that node. That node may have a neighbor cache of other V6 nodes on the network, or if you could somehow, with the router, use a read-only SNMP community string, you could read the neighbor cache out of the local router to find other hosts on the network. I mean, but the attacker isn't just going to use one technique. They're going to use a variety of techniques in combination to facilitate reconnaissance. Now, in server farms, you are going to address servers, :3, :4, :5. They're going to be statically assigned. They're going to be put into the DNS with quad A records and the appropriate IP6.ARPA pointer record. So for server farms, servers are easy to find. And routers are easy to find because the routers will be ::1, and the routers are going to be sending routing advertisements. They're going to be sending multicast listener discovery messages out on the LAN. So routers are chatty. The router is going to be easy to find, trivial to find. So there's no sense in hiding those systems. But we would want to obfuscate the interface identifier of nodes on the LAN and nodes on, let's say, access networks, end-user access networks. We would want to randomize the interface identifier if possible. And most DHCP6 servers do that already. So finding a host to attack is kind of an issue. So I said IPv6 uses ICMP for Slack, for neighbor discovery protocol. So your networks today don't have routing advertisements on them. And so your hosts, they don't have IPv6 addresses assigned. They haven't been clued into who the default router is. They haven't heard that routing advertisement that tells the operating system how to go about assigning its IPv6 address. Should it use DHCP? Should it use stateless address auto configuration? It's not hearing that information. But what if someone came along and generated a single routing advertisement packet and sent it on your LAN? Your hosts would then hear that routing advertisement and then act on that. Like, oh, our network became IPv6 capable. I'm an IPv6 capable node. I'm going to hear that routing advertisement, and I'm going to use the system that sent that routing advertisement as my default gateway. So if an attacker could generate a rogue RA routing advertisement on LAN, it could wake up the dormant IPv6 protocol stack in all of your hosts, in your server farms, in your access networks, on your wireless networks, and then perform a man-in-the-middle attack. So essentially, a attacker sends a rogue routing advertisement message out onto this wire. Your hosts configure themselves with IPv6 for what, the flags that are containing the routing advertisement, and then use the attacker as its default gateway, and it can just perform them in the middle. And now your host thinks it's v6 capable. When you go to Facebook, Facebook over IPv4 looks remarkably similar to Facebook over IPv6, and the end user doesn't know. They don't know that the transport behind the scenes was actually IPv6. So easy to do a man-in-the-middle attack with IPv6. And then this device could either create a tunnel out to the internet, could tunnel the v6 traffic out to the internet, or could, in some other way, be bridged out to the IPv6 internet, or doing another gateway type function. So it would be v6 native from the victim to the rogue system on the network generating rogue routing advertisements. This device could have a tunnel out here out to the internet or something like that, or some other back channel way of encapsulating and wrapping the v6 traffic into v4, getting it to another place, unwrapping it, and sending it natively to AmericanExpress.com or what have you. So you can also have attackers on the LAN forge neighbor solicitation, neighbor advertisement messages to confuse, ARP, or confuse neighbor discovery protocol. It's the same problems that we have today with ARP. And everyone here sleeps pretty well at night, right? Or maybe not. But I mean, we have these issues. There's all kinds of ARP funny business you can do on LAN. And largely, many organizations, even today, haven't done anything to do DHCP snooping, dynamic ARP inspection, first hop security for IPv4. Why would they do any of these things for IPv6? Because most people are convinced, I'm not running IPv6. Why would I turn on those IPv6 features on the LAN? And the way, so part of the motivation here is that an attacker wants to do a man-in-the-middle attack, either to snoop traffic or capture some passwords or things like that. And the motivation is not to raise awareness, because the attacker has already compromised the system on the LAN. So this is a big requirement. The attacks presume that the attacker is already on net. If the attacker is already on net, they're not motivated to raise awareness that they're there. So generally, if you were to do an ARP attack or do something like this, the attacker would turn it on for a few minutes, be a man in the middle. If something goes wrong, the user's like, something's not working here. I better call the help desk. By the time the end user figures out the help desk phone number, calls them, oh, it wasn't working just a minute ago, but now it seems to be back. Oh, okay, no big deal. And the help desk person doesn't think anything of it and hangs up the phone. I mean, so it's short windows of these kinds of things that may be happening. It's not long-lived. And so the attacker could do these neighbor discovery protocol attacks for short windows of time, act like a man in the middle for a brief period, capture what they need to, still remain stealthy. You can force nodes to believe that other networks are on the link. You could send a routing advertisement for Google's address space to convince nodes on the network that Google is local, and so they should send all their traffic along the local LAN, and then the man in the middle just forwards them on, and so forth like that. So lots of things with neighbor discovery protocol on a LAN that an attacker could leverage. So there's this IPv6 attack toolkit. Mark Van Hauser, who's from Germany, created this toolkit in 2005. Many years ago, it wasn't well documented, but over the years, 9 years, it has been more and more refined, more tools have been added, more contributions have taken place to develop new tools. Now it's a pretty comprehensive suite of about 60 different utilities. Current version is 2.5. There's some scanning, some reconnaissance tools built into it, like I described. Live6 communicates with an all nodes multicast group address on the network. There's DNS enumeration. There's local discovery, like detect new. Basically, it listens for any system that sends a neighbor solicitation for itself as part of it doing duplicate address detection, listens for those, and then records who's on the network. There's traceroute, there's other helper tools, there's a variety of man-in-the-middle tools. And these, either do the ICMP redirects, which is ICMP6 redirects, which is the same as ICMP redirects. Fake advertise 6. You can generate, fake router 6, fake router 2.6. are the methods and tools to create fake rogue routing advertisements. It could fake a DHCP server, fake DNS, fake mobile IPv6 communications, other testing tools. So the tools are kind of broken down into these categories. There's lots of denial of service attack tools as well that flood volumes of IPv6 traffic on the LAN, or flood traffic to a particular destination to affect a particular, Linux version, or create these traffic packets in certain ways to either create a denial of service attack for, the system in the middle, or the system that receives the volume of traffic. DOS new IPv6 is kind of funny. This is something you could use on your friends. So when the system boots up, it does this duplicate address detection, and it essentially sends the neighbor solicitation for its own address and listens to say, does anybody have this IP address that I'd like to use? If it doesn't hear back a neighbor advertisement, it assumes the address is not a duplicate, it's unique, and can use that interface identifier. This tool listens for those messages and says, yeah, I'm using that address. And the operating system is like, man, 1 in 18 quintillion, what are the odds I should go play the lottery? So then it says, okay, I'll come up with another interface identifier, it sends another one, and the attacker's like, yep, that one's used too. And it just, perpetually does that and keeps the system off the network. So you see, the funny business you could do on an ICMPv6 enabled network. So there's a variety of different flooding utilities. So it's a pretty comprehensive, robust toolkit, and now this toolkit is now in Kali Linux 106 by default. So if you're using Kali Linux, look for these tools. They're in the menu structure. You go through and look at different tools. You'll see that Active Choice IPv6 toolkit is embedded in. As well as inside Kali Linux, there's a tool called Arrayo, which is an open source version of Terrayo, which you can use to create a back channel. Or you could run your interpreter over Arrayo, or whatever. And you don't have to use the standard Terrayo port, UDP 3544. You could run Arrayo on another port, like 53 or something like that. So Fernando Gant, a friend of mine, IPv6 security researcher from Buenos Aires, Argentina, he's created this IPv6 toolkit, but it's a slightly different toolkit. Instead of creating lots of little tools that do very specific things, he has a few tools that are generic and then have lots of parameters that can configure and create many different types of packets. So he has let's say, ICMP6 command, and ICMPv6 can then be modified with many different parameters to generate a variety of different packets, all of that type. Jumbo6 creates, jumbograms. You can have really big messages in IPv6. Still, on the interface, you still have to follow the MTU size, the maximum MTU size on the LAN, but then it does fragmentation. So NA6 sends neighbor advertisement messages. On the next slide, there's a tool called NS6 that sends neighbor solicitations. RA6 sends routing advertisements. So you'll use these tools in combination with each other to create the kind of effect that you want. Pretty well documented. Fernando's always going to make updates as needed. And so 153 is where you get his toolkit, download it, play around with it, and stuff like that. Last year at DEF CON 21, another Spanish person named Cheno Alonso also created this tool called Foca, which is basically a weaponized WinExe script kiddie packaged up version of some of these same IPv6 attacks. It does IPv4 and IPv6 man-in-the-middle type of attacks, and does DNS hijacking and WPAD proxy attacks and things like that. It can send rogue routing advertisements. It can do ICMP, v6 flooding, and DOS. It activates and it shows a big long list of all of the discovered nodes on a network, so it also facilitates some of the discovery and reconnaissance. The evil Foca system running equal Foca. Foca means seal in Spanish, so it's like a little fat seal. That's the picture. I don't think it means something else. So it sends these different kinds of packets, and it basically it's very easy to use, GUI. This is all very simple to use. And here's where you can download it. You can go to this website. It asks for your email address. Don't use a real email address. And then there's a YouTube video to see how it works. Okay, so there's a variety of IPv6 attack toolkits that leverage creating crafted packets of different types. They create crafted packets on a LAN and have this type of effect. So how would we detect a rogue advertisement, or how would we prevent a rogue advertisement on our network? Because up until this point, most enterprises haven't taken any steps to secure IPv6. But wouldn't you want to know if someone was generating rogue routing advertisements on your networks today? Because today you lack visibility into what's going on your LAN. Maybe you don't care so much about end users or wireless networks, but you probably care a lot about what's happening in your data center, or your lights out facility, or the cloud infrastructure that you have that you don't really own. You lease, or you borrow, or you rent. You can prevent unauthorized access. Federal organizations like in this room have mean guys with guns at the door, and physical access. But you saw how easy it was in the video this morning, how easy it is to bypass physical security. We can disable and use switch ports. That's a best practice. We don't want anyone just to plug into, let's say, this cable right here. We could use 802.1x. Many organizations that use 802.1x may just use simple MAC bypass, which any college kid would know how to bypass. But the nice thing about 802.1x is it's a technique that works for v4 and v6. Based on user authentication, it would activate the port, and when the port comes active and the port gets assigned to a VLAN, then that VLAN could then work v4 and v6. MACsec, TrustSec don't have much v6 capability, but they need to be able to detect this type of stuff. Port security, you can limit the number of MAC addresses on a port, but the host uses the same MAC address for v4 and v6. And it just looks like an Ethernet frame. It's an Ethernet 2 frame that has the source and the destination MAC address. They're the same, but the difference between a v4 and v6 packet is 0800 is the type, or 86DD is the type in an Ethernet frame. 86DD indicates that it's an IPv6 packet inside of an Ethernet frame. Private VLANs could be used. Most network access control, network admission control systems only work for IPv4. They don't do anything for IPv6. And you can run wireless LANs in API isolation mode. You can create a port-based ACL that basically restricts routing advertisements coming in from the downstream port. So you can set an access list that says, deny routing advertisements, deny rogue DHCP v6 services, and apply that inbound to your end users' downstream ports on your Ethernet switch, and allow all other IPv6 packets. But there's a technique called RA guard, RFC 6105, that is embedded, it's a function that's embedded inside of the Ethernet switch that allows the routing advertisement to be sent from the legitimate router down to all the nodes on the network, but prevents the illegitimate or rogue routing advertisement from being sent into the Ethernet switch and forwarded, like a multicast, forwarded out to all the other nodes on that layer 2 network. I like this little picture here. I'm from Colorado. He's not smoking a cigarette. So NDPmon, RA1D, RA50, 6guard, 6mon, a whole bunch of tools that are basically like the IPv6 version of ArcWatch. And so ArcWatch just tells you who's on the network, who's generating these rogue routing advertisements, who's sending router solicitation messages. So there's tools that you can run to find these things out. The other way that attackers can leverage IPv6 is by generating rogue packets with invalid extension headers. Between the IPv6 header and the upstream TCP your protocol data are extension headers that can optionally be added. These headers could be manipulated in different ways and created to create either a denial of service attack or some issue or a resource consumption attack for a system along the traffic path or the destination that receives these. And many of the tools that you saw, the Actor Choice Toolkit, SI6, others can generate these kinds of traffic packets, these traffic attacks easily, like SCAPI6. You can craft, any kind of IPv6 packet just like you can craft a v4 packet, with the thought here being that vendors might not have implemented IPv6 as robustly as they have with IPv4, or maybe not all of the ways that a packet could be blocked with IPv6 the same as it would block with IPv4. And we don't want to be overly aggressive at filtering ICMPv6 because it's needed for end-to-end communication, for path into discovery, and we need neighbor solicitation messages to work on the outside of our firewalls because that's how you learn about your next hop and you maintain next hop reachability. So with IPv6, you have twice as much attack surface. You have to defend your v4 and your v6 attack surface equally well. And the attack rules is keenly aware that you have a site or a system that's accessible over v4 or v6 because when they did a DNS query, it came back with a record and a quad record. And so when you're running dual stack, you have twice as much work to do, twice as much vulnerabilities. But if you have a XSS vulnerability and you fix it inside of the web application, you fixed it for v4 and v6. That's the good news. But you may have issues where if your web application firewall is only looking at the v4 connections and you have an XSS vulnerability over IPv6 that the WAF isn't detecting, then the attacker is going to go for the weakest link. So you want to look for and you want to achieve feature parity. You want to learn about IPv6, learn about the differences in how IPv6 works compared to what you're used to, and you want to achieve equal protections, but this may be difficult because the vendors might not have given you all of the tools that you need. You may be relying on an external scanning vendor, but the scanning vendor is only scanning your sites or your web apps for cross-site scripting, SQL injection attacks over IPv4 transport. They aren't looking at IPv6 transport. You may be doing code review, but maybe the code review is just v4 code review, not v6 code review. Not knowledgeable about that in any way. So ask your vendor about what v6 features they have or what they lack, and you want to line them up in an order. We need this we need this type of logging to be taking place. Do you log that for v4 and v6? And you go through your big long list and say, do I have feature parity, or is there something I'm missing with IPv6? You want to be knowledgeable about it. So IPv6 is really no more or less secure than IPv4. It's really a lack of experience and knowledge in the industry that's the issue. There's a protocol that's running inside our environments that we haven't largely taken steps to secure, but we need to be aware that it's there and maybe start to perform some security mitigation of the protocol ahead of when we roll it out. We want to perform granular IPv6 filtering at the perimeter. We want firewalls to have that kind of filtering. We want network function virtualization systems to have that kind of granularity. We may use a network access control system to protect v4 and v6. At the perimeter, we may want to do anti-spoofing, unicast RTF filtering, do proper ingress-egress filtering for v6 as we roll it out. We would prefer manually configured tunnels, actually. We prefer dual protocol over manually configured tunnels. We prefer manually configured tunnels over dynamically configured tunnels. But you may want to disable tunnel techniques traversing through your perimeter if they're not part of your transition strategy. You're going to leverage IPsec for a lot more than in an IPv6 environment than you leveraged in an IPv4 environment because you don't have to do NAT traversal. You can do AH and ESP together. Your IPsec deployments are going to be stronger with IPv6. And you're going to deny packets for transition techniques that aren't in use. and there's a new draft coming out that's going to give you a lot more guidance on operational security for IPv6. So I'm out of time, but there's a book that I authored with Eric Bank, a distinguished engineer from Cisco, that has a lot more details about how these tools work, how to create these packets, and how to create filters and access lists and things to block these types of attacks. So here's where I can be found on the internet, and then the things I write about, and lots of articles I write about in security at these locations. I don't think I have any time for questions, but I'll be around after this, and if anyone has questions, I'd love to talk to you about IPv6 security.